Hi, I'm Bailey Jones, and I will be going over universal gravitation with you today. My major is dental hygiene.
Hello, my name is Paris, and we are doing Newton's universal law of gravitation.
Hello, my name is Jake Rhodes. My major is instrumentation technology, and our group is giving a presentation on universal gravitation.
Hi, my name is Tessa Parrish. I'm finishing up my Associates of Science degree at the end of the year, and at the beginning of the year we'll be applying to the dental hygiene program. Our group will be presenting Isaac Newton's law of universal gravitation.
Universal gravitation. Universal gravitation, as described by Newton's law of universal gravitation, states that every particle attracts every other particle in the universe with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This law explains why planets orbit the sun. The sun's immense mass exerts a strong gravitational pull. Why apples fall from the trees, Earth's gravity pulls them down, and why the tides on Earth are influenced by the moon and sun. Their gravitational pulls affect the oceans. It's a cornerstone of our understanding of the cosmos.
Universal gravitation is a fundamental concept with wide-ranging applications across numerous scientific fields. Here are some key areas. Astronomy and astrophysics. This is arguably the most prominent application. Understanding universal gravitation is crucial for explaining planetary motion, stellar evolution, galactic dynamics, and the formation of a large-scale cosmic structures. Celestial mechanics. This field specifically deals with the motions of celestial bodies under the influence of gravity. Geophysics. Earth's gravity plays a crucial role in shaping its internal structure and influencing surface processes. Space exploration. Accurate calculations of gravitational forces are essential for launching rockets, planning interplanetary trajectories, and navigating spacecraft. Physics in general. This is a universal gravitation serves as a foundational principle in classical mechanics and is a stepping stone towards understanding more advanced concepts like general relativity.
Sir Isaac Newton was an 18th century pioneering English scientist whose work transformed physics, mathematics, and astronomy. Born prematurely, he showed remarkable intellect early on and studied at Trinity College, Cambridge, eventually becoming a professor. His most famous contribution to science is the law of universal gravitation, which he explained in his 1687 masterpiece Principia, in which he also introduced his laws of motion, foundational to classic mechanics. Newton also made major advances in optics, producing the first reflecting telescope and proving that white light is made of colors. He developed calculus independently of Leibniz, sparking a famous rivalry. Beyond science, Newton served as a master of the Royal Mint and dabbled in alchemy and theology. Despite a complex personality and sometimes tense relationships with his peers, his legacy as one of history's greatest scientific minds endures.
Newton's journey to developing the law of universal gravitation was not accomplished through a single physical experiment, but rather a combination of mathematical reasoning, careful study, and astronomical data. He imagined the moon as constantly falling towards Earth, just like the apple, but moving sideways fast enough to stay in orbit. By comparing the acceleration of objects on Earth to the motion of the moon, he found that gravity weakened with the square of the distance, a relationship that matched astronomical data. Newton used Kepler's laws of planetary motion, acknowledging the force keeping planets in orbit must decrease with the square of the distance from the sun and must depend on mass.
Original experimental process. The knowledge led Newton to propose his famous equation shown in the bottom right hand corner, that gravitational force is proportional to the product of two masses and inversely proportional to the square of the distance between them. F equals the gravitational force between two objects, G the gravitational constant, M1 and M2, the masses of the two objects, are the distance between the center of the two objects, as you can see in the graphs.
Difficulties and complications. Mathematical tools still in development. To describe motion and gravity, Newton needed mathematical tools that did not exist yet. So he developed a framework he called fluxions, which would later be known as calculus. Lack of precise data. Newton had to rely on estimates for planetary distances, orbital speeds, and masses. Resistance and isolation from other scientists. Many scientists were skeptical and believed his theory controversial. Because of this skepticism, Newton did not publish his research for over 20 years. It wasn't until 1687 that he published his findings named Principia Mathematica.
The motivation behind the experiment. Newton wanted to know why some objects fall to Earth while planets stay in orbit. The iconic story of the falling apple sparked his curiosity of whether the same force could also be responsible for keeping the moon in the sky. What he was aiming to do was prove that the laws of nature apply to both Earth and the cosmos.
What were the benefits to this discovery? Previously, people believed celestial objects followed different rules compared to the things on Earth. Newton's universal law of gravitation showed that all parts of the universe are governed by the same laws. We can now predict and track celestial phenomena such as eclipses, planetary orbit, comet paths, and tides. It also made improvements to star navigation. But the biggest thing of all, it birthed an entirely new field called celestial mechanics.
This slide explains a modern version of the Cavendish experiment, which is used to measure the gravitational constant G through a torsion balance setup. Here's a simplified summary. Purpose: to demonstrate universal gravitation and calculate the gravitational constant G by measuring the attraction between small masses in a lab setting. Setup: a lightweight rod with small masses at the end is suspended horizontally. Large masses are placed near the smaller ones to create a gravitational pull. An optical system, mirror and light beam, detect minutes deflection of the balance. Procedure: the balance is brought to equilibrium. The deflection caused by gravitational attraction is recorded. The period of oscillation helps determine the torsion constant. Calculation using Newton's law allows determination of G. Challenges: it's a very delicate experiment due to the weak gravitational forces involved, which can be affected by minor environmental factors. Significances: despite its simplicity, it provides accurate values for G and helps us understand gravitational interactions and fundamental physics.
Modern advancements. Advanced cryogenics reduced thermal noise and improved material properties. Sophisticated lasers and interferometry increased sensitivity and enhanced data acquisition. Stronger metals and alloys reduced drift and creep and improved dimensional stability. Improved handling of toxic or radioactive substances provided safer environment and expanded the possibilities. The combination of these advancements has led to a significant reduction in the uncertainty associated with measuring G. While the original Cavendish experiment was a monumental achievement, modern versions have refined the value of G by several orders of magnitude, approaching uncertainties of only a few parts per million. The improved accuracy has profound implications across many fields, from fundamental physics and cosmology to geodesy and geophysics. The quest to measure G continues, driving further innovations in experimental techniques and technologies. Some
of the many modern benefits of our understanding of universal gravitation includes satellite navigation, GPS. If you've ever wanted to go somewhere and you didn't know where that place was, you probably use GPS. The way that works is they have satellites up in the sky, and they are shooting down beams and detecting the differences in gravity along the way. This is because different parts of the Earth have different levels of gravity, and it can detect those. Space exploration. You want to get into space? Gravity doesn't want you to. So you got to know how to counter that, what kind of force you need. But if you use the right kind of force and the wrong mode of transportation, so you have to know how to handle the stressors of gravity as well. Geography and geophysics. Gravity allows us to locate a lot of natural resources as well as predict natural disasters and things like earthquakes and avalanches. We can predict those using universal gravitation. And most importantly, it's a cornerstone of fundamental physics. There's ongoing research into it. We still don't fully understand gravity. We know how to read it. We sort of know what it does, but we also don't really know what it is.
Looking to the future, how will scientists use this information in research? They could look into more precise measurement for G, or gravitational constant, testing general relativity in extreme, quantum gravity, understanding dark matter and dark energy, gravitational wave astronomy, gravitational wave detection for early warning systems, fundamental meteorology, advanced navigational systems, improved gravity sensors, and spacecraft propulsion and navigation.
Relevance of question to topic. If the moon were twice as far from the Earth, how would the gravitational force between them change? The question applies Newton's law of universal gravitation. It helps show how distance directly affects gravitational force. We're not changing the mass, just the distance. This isolates the emphasis, the inverse square part of the law.
Benefits of understanding the question. This helps students visualize how changing distance can affect gravity. This also teaches the power of inverse square relationships, builds problem-solving skills with formulas, and connects to the real-world ideas like orbits, tides, and space travel.
The process of writing our question. We started by looking for a what-if question, a theoretical scenario, something that's conceptual enough to be realistic, but also not necessarily possible in the real world. There were a lot of things that we considered along the way, different ideas that we threw around, like what happens if Earth's mass doubles, or what if the force between two objects is unknown. But we threw a lot of these out because we felt like they were either too vague or unoriginal.
How is this question unique? Textbook examples usually have you plug information into an equation. This question changes the relationship and leads to a big realization. Doubling the distance equals 1/4 the original gravitational force. This question makes the students think deeper instead of just solving.
Chart of distances. The table compares gravitational force at the moon's normal distance versus double the distance. Since gravitational force is inversely proportional to square of the distance, doubling the distance reduces the force by a factor of 4. F2 equals F1 divided by 4. That demonstrates how increasing distance significantly decreases the gravitational attraction between two objects, as you can see in the graph.
Formula explained. Newton's law of universal gravitation reads force equals gravitational constant times mass of object 1 times mass of object 2 divided by the distance between centers of the masses. If we double R, the force will become 1/4. If we triple R, the force will become 1/9. And if we cut R in half, the force will become 4 times.
For our question, we asked if the moon were twice as far from the Earth as it is now, how would the gravitational force change? And that's an important section of the question. How would the force change? This required that we compare the force of gravity both before and after we double its distance. This actually requires us to use Newton's universal gravitation law twice. But the trick is that what we're looking for is F in this case. So, because we have the gravitational constant, which never changes, and we already know the mass of our first object, the moon, and our second object, the Earth, and we know the distance between them, and we also know the distance we're going to double it to. Force is the only factor missing.
Step 3. This equation shows that gravitational force is inversely proportional to the square of the distance between two objects. If the distance r is multiplied by 2, then the force becomes F equals 1/4 of the original force. Step 4. Calculating the gravitational force in both scenarios. G equals 6.674 multiplied by 10 to the negative 11th power. M1, the Earth, equals 5.97 multiplied by 10 to the 24th power kilograms. M2, the Moon, is equal to 7.35 multiplied by 10 to the 22nd power in kilograms. And R equals 3.84 multiplied by 10 to the 8th power m.
Continue. Step 5, original force. As you can see, the equation is wrote out here. Step 6, double force at double the distance. Also, the equation is listed here.
On step 7, we have the final comparison. We have F2 equals F1 divided by 4 equals 1.986 times 10 to the 20th power divided by 4 equals 4.965 times 10 to the 19th power n. If the moon were twice as far from the Earth, the gravitational force would be 1/4 as strong.
accuracy. The math checks out. The force is 1/4 as strong when distance is doubled. This directly proves Newton's law in action. It's relevant because it shows how even simple changes in space can affect things like the moon's orbit, satellite designs, space mission planning. Small changes in space equals big changes in gravity.
Conclusion. After examining universal gravitation from multiple perspectives, the findings across each section offer valuable insights. Understanding the implications of this topic isn't just academic exercise, it carries real-world consequences. This section brings together the report's key takeaways, outlines, and specific observations based on the team's research, highlighting what matters most.
Scientific contributions and legacy. Sir Isaac Newton was an 18th century English polymath and graduate of Trinity College, Cambridge, where he later became warden. He made groundbreaking scientific contributions despite lacking precise SI measurements and finely calibrated tools. Newton worked with unstandardized observations and rudimentary instruments but excelled at accounting for imprecision. He synthesized his own 3 laws of motion, Galileo's work on motion, Kepler's laws of planetary motion. This led to his formulation of the law of universal gravitation, which states every 2 masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them.
This theory explained planetary orbits and allowed for accurate predictions of planetary motion. It influenced several fields of science, including astronomy, astrophysics, celestial mechanics, geophysics, and it laid the groundwork for Einsteinian science, I believe it's called. Beyond gravity, Newton also invented the reflecting telescope, and he developed the rate and area method for calculus. Calculus, of course, being one of the building blocks of physics.
Opposition and reluctance to publish. 1. Conflict with Robert Hooke. Hooke criticized Newton's optical theories in 1672, instigating the first of 3 major clashes between the two. Their second major conflict occurred in 1679 during their correspondence, where Hooke claimed a theory of circular motions compounded by a direct motion and attractive one to the center. This implied that Hooke had priority in formulating key ideas related to planetary motion, ideas that later became crucial to Newton's theory of gravitation. The relationship ultimately degenerated into a bitter and burning hatred, following the publication of Principia Mathematica. This hostility fueled Newton's defensiveness and made him increasingly reluctant to publish controversial ideas during Hooke's lifetime.
Opposition and reluctance to publish. Fear of public criticism. Newton's conflict with Hooke over optics in 1672, described as a somewhat hasty and rather sharp criticism by Hooke, triggered a pattern of withdrawal. As a result, Newton obstinately refused to publish his optics during the lifetime of Hooke, choosing instead to wait for Hooke's death. He was described as awaiting patiently and confidently the disappearance of his foe. This episode reveals Newton's extreme sensitivity to criticism and how it influenced the timeline of his major publications. Only after Hooke's death in 1703 did Newton finally release optics in 1704.
Profound impact. Our group learned that Isaac Newton's discovery of universal gravitation had a much more far-reaching impact than was initially thought. On his journey to uncover the laws of the universe, he created an entirely new branch of mathematics, calculus, to prove his theories. This breakthrough in understanding and mathematical advancement will later become the foundation of modern physics and engineering.
Closing thoughts. Universal gravitation is a topic that has taken countless scientists many years to understand as well as we do now. Yet, even with our expanded understanding, there are still questions and oddities that science has not yet been able to answer, such as what gravity is at a fundamental level, how and if it fits into quantum mechanics, why gravity is so much weaker than other fundamental forces, and what the true nature of dark matter and dark energy might be. But science is an ongoing process of theories, tests, answers, and sometimes just more questions. The very nature of universal gravitation speaks to the part of us that wants to strive, to be more than what we are, to understand the world, perhaps in an attempt to better understand ourselves. And who knows, maybe in a century we will know everything there is to know about gravity, but the truth is, people don't seek final answers. They seek the journey, because if we're honest with ourselves, we don't want to know. We want to explore. And physics in more ways than one is the final frontier.